This video will continue to discuss what happens at the synapse. By the end of this video, you should be able to explain the difference between an action potential and a graded potential, and also the difference between an EPSP and an IPSP. So an action potential, remember we've discussed this previously, so if you need to refresh your memory on what the action potential is, you can refer back to earlier videos. But just to remind ourselves, an action potential occurs in the axon, and remember it's traveling away from the cell body down the axon, that long extending fibers, to those axon terminals. It is an all or none phenomenon. And what that means is it's the same amplitude down the entire axon, regardless of the intensity that stimulates it. So once the cell gets to threshold, and this is our threshold here for this cell, we have an action potential. This action potential can travel long distances, and it's always going to be the same amplitude and the same speed. It does not decay over time. It doesn't get weaker over time or space. And it's continuously regenerated. So we talked about how it propagates down the axon, how that myelin sheath helps to speed up that propagation because it's only regenerated at the gaps in the myelin sheath called the nodes of Ranvier. So this is just a kind of a brief summary reminding us of what an action potential is. Now let's compare that to a graded potential, because that's what we're going to be talking about in this module. So a graded potential occurs at the synapse. So the action potential traveled down the axon. Now we're here at the synapse, and we're going to have in that postsynaptic neuron a graded potential. It does decay over time and space, so it does get weaker over time. So as the more time passes, the weaker that potential is going to be, and over space. The farther away from that initial potential, the weaker that potentiation will be. And so we're going to talk about two: an excitatory postsynaptic potential, or an EPSP, so an excitatory postsynaptic potential, and an inhibitory postsynaptic potential, an IPSP. So if you remember that the PSP stands for postsynaptic potential, inhibitory is I, and the E is for excitatory, and we'll learn the differences between those in the rest of this video. So this is just showing you here how it decays over time and space. So here you have a presynaptic terminal, and it's synapsing here with this dendrite. And you see as it comes in here, if we record in the dendrite of the receiving neuron, this is that first little potentiation that we're going to see. But as those ions diffuse away, we can see that potentiation gets weaker and weaker the farther out we go. So this is over space, but the same thing would happen over time. So an excitatory postsynaptic potential is a graded depolarization. In order for this depolarization to occur, when the neurotransmitter binds the receptors on those postsynaptic cells, gates for sodium ions open up and sodium flows into the postsynaptic neuron. And that's what this diagram is showing you. So here again, we have that action potential traveling down the axon. It reaches that axon terminal, and we'll discuss a little bit later about what happens at the synapse for that neurotransmitter to be released. And then it's going to bind here on this postsynaptic membrane. It binds a receptor. Sometimes there are sodium channels that open up. So here these little green dots are the neurotransmitter, binds the receptors, opens up a sodium channel, and in order for an EPSP to occur, that sodium flows in. And remember, sodium flowing into the cell is going to do just what it did during the action potential, and it's going to cause a depolarization. Now, how much sodium goes into that postsynaptic dendrite or neuron depends on how much and how big that depolarization is. Now remember, if at the axon hillock that cell gets to threshold, an action potential will travel down that receiving neuron's axon. So this is an EPSP, and EPSPs make cells more likely to fire an action potential. Now let's compare that with an IPSP, or an inhibitory postsynaptic potential. Graded hyperpolarization. And in order for this to occur, we see down here that the neurotransmitter, again a different color now because it's a different type of neurotransmitter, is going to bind a receptor, and it's going to open ion channels for chloride ions. Chloride is negatively charged. When that chloride ion that's negatively charged enters that postsynaptic neuron, we see a hyperpolarization. Remember that hyperpolarization is going farther away from zero. So this IPSP is going to suppress excitation. So it can cancel out an EPSP, or it can just make it less likely that that receiving neuron will fire an action potential. So it inhibits the cell from firing action potential.